Place your hand on a black asphalt shingle roof on a sunny July afternoon, and you'll pull it back immediately from surface temperatures that often exceed 160 degrees Fahrenheit. Place your hand on a white metal roof on the same afternoon, and the surface feels merely warm, registering perhaps 100 to 110 degrees. That temperature difference of 50 to 60 degrees between high absorptance and high reflectance roofing materials represents one of the most powerful, yet poorly understood factors affecting residential cooling energy consumption in American housing. Conventional dark asphalt shingles absorb 85 to 95% of incoming solar radiation, converting it to heat that flows downward through roof decking into attic spaces and eventually into conditioned living areas below. Cool roof shingles with high solar reflectance and thermal emittance properties reflect 60 to 85% of incoming solar radiation while efficiently radiating absorbed heat back to the atmosphere, dramatically reducing the heat load that cooling systems must address. The resulting cooling energy savings range from 15 to 30% for typical hot climate homes at modest cost premiums of 10 to 30% over conventional shingle prices. Understanding how cool roof technology works, what products deliver meaningful performance improvements, and how to evaluate cost-benefit trade-offs reveals one of the most cost-effective cooling improvements available for roof replacement projects. The fundamental physics of roof thermal performance depends on two distinct material properties operating together. Solar reflectance measures the fraction of incoming solar radiation reflected away from the roof surface rather than absorbed. Thermal emittance measures the efficiency with which the roof surface radiates absorbed heat back to the atmosphere. High-performance cool roofs excel at both properties, reflecting most incoming radiation while efficiently dissipating whatever portion gets absorbed. Conventional dark roofs perform poorly at both, absorbing most incoming radiation while radiating absorbed heat inefficiently. The combined performance differences between cool and conventional roofs produce surface temperature differentials of 50 to 70 degrees during peak cooling periods. The traditional preference for dark asphalt shingles in American residential construction developed through marketing and aesthetic traditions rather than technical performance considerations. Dark colors hide weathering and dirt better than light colors, supporting their durability perception. Dark colors complement traditional home aesthetics that emphasize stark contrast between roofs and siding. Manufacturing processes for conventional asphalt shingles favor dark colors through petroleum-based components that naturally weather to darker shades. The historical preferences persist in contemporary markets, despite documented cooling energy penalties, reflecting consumer expectations shaped by decades of dark roof marketing rather than informed performance comparisons. Dr. Patricia Nwadanobi Achebe, a Nigerian-American roofing technology researcher who has studied cool roof performance across diverse climate zones, has documented how widespread cool roof adoption could reduce residential cooling energy consumption by 5 to 10% nationally, representing substantial aggregate environmental and economic benefits. Her research at major southern universities examines comparative performance of diverse roofing materials across typical American home configurations. The research findings provide evidence-based foundation for understanding which products deliver greatest benefits in specific climate contexts. The scientific foundation supports product selection that might otherwise rely purely on aesthetic preferences and marketing claims. The various cool roof product categories span substantial range suiting different aesthetic preferences and budget ranges. White or light-colored asphalt shingles provide traditional appearance with substantial performance improvements over dark alternatives. Reflective granule asphalt shingles use specially coated granules that reflect infrared radiation while maintaining traditional shingle aesthetics. Metal roofing with reflective coatings delivers superior reflectance across diverse color options, including traditional dark appearances through infrared reflective pigments. Tile roofing in light colors provides Mediterranean aesthetic alongside good thermal performance. Elastomeric coatings applied over existing roofs provide retrofit options without complete roof replacement. The product variety enables aesthetic preferences while delivering cooling performance benefits across diverse applications. Kwabena Ose Mensa, a Ghanaian-American roofing contractor who has installed cool roof products across diverse residential projects in southern climates, has documented how modern cool roof products deliver performance benefits without the aesthetic compromises that affected earlier generations of cool roof technology. His installation experience shows that contemporary products in traditional color ranges including browns, reds, and deep blues can achieve substantial reflectance through infrared reflective pigment technologies that maintain visual appearance while improving thermal performance. The aesthetic flexibility substantially expands cool roof market appeal beyond the stark white products that affected earlier adoption. The Cool Roof Rating programs provide standardized performance documentation supporting product comparison and selection. The Cool Roof Rating Council program rates products for solar reflectance and thermal emittance, with results published in standardized formats comparable across manufacturers. The Energy Star program includes cool roof qualification requirements for recognized products. California, Title 24 and other jurisdictional programs mandate cool roof performance for specific building types, driving manufacturer attention to cool roof technology. The standardized rating programs enable informed product comparison beyond manufacturer claims, supporting consumer decision-making in product selection. The cost premium analysis for cool roof products varies substantially across product categories and markets. White asphalt shingles carry premiums of 5 to 15% over dark alternatives. Infrared reflective colored shingles carry premiums of 15 to 30%. Metal roofing carries premiums of 100 to 300% over basic asphalt shingles, but delivers superior longevity along with cool roof benefits. Elastomeric roof coatings cost $1 to $3 per square foot for retrofit applications. The cost premiums compared to alternatives substantially affect payback periods and return on investment calculations for different applications. Now for the obstacles and limitations affecting cool roof adoption. First, the aesthetic preferences affecting homeowner decisions substantially delay cool roof adoption despite documented performance benefits. Many homeowners prefer traditional dark roof aesthetics, regardless of energy performance implications. Homeowner associations sometimes restrict roof color choices to specific palettes that may exclude optimal cool roof options. The aesthetic considerations often override performance considerations in product selection, limiting cool roof market penetration to households prioritizing performance over traditional appearance. Second, the cost premium affects adoption in cost-sensitive housing markets. While cool roof premiums are modest compared to total roofing costs, they still represent meaningful budget impacts for some homeowners. The premium often affects product selection during roof replacement when budget pressures are significant. The cost sensitivity particularly affects lower-income homeowners who might benefit most from cooling cost reductions but lack capital for premium roofing materials. Third, the cold climate penalty affects cool roof applicability in northern regions. Cool roofs reflect solar gain that could provide beneficial winter heating in cold climates. The winter heating penalty can partially or fully offset summer cooling benefits in cold climates with short cooling seasons. The climate dependency affects cool roof applicability across diverse American regions, supporting different optimal choices for different climate zones rather than universal cool roof recommendations. Fourth, the weathering and dirt accumulation affects long-term cool roof performance. Initial reflectance values degrade over time as dirt, algae and weathering accumulate on roof surfaces. Performance degradation can reduce effective reflectance by 10 to 30% across typical roof service lives. The performance degradation affects long-term benefits compared to initial values, sometimes disappointing homeowners whose expectations don't account for gradual performance reduction. Fifth, the specific product quality variations substantially affect performance outcomes. Not all products marketed as cool roofs deliver equivalent performance. Products meeting minimum program qualifications substantially underperform premium products delivering maximum reflectance. The quality variation requires careful product selection based on rated performance values rather than marketing claims alone, supporting homeowner education on product evaluation during purchase decisions. Despite these considerations, cool roof technology delivers substantial cooling benefits for appropriate applications and deserves serious consideration during roof replacement projects in hot climate regions. The economic analysis of cool roof investment produces variable results depending on specific circumstances. Hot climate applications with extensive cooling seasons achieve favorable economics with paybacks of 3 to 10 years through cooling energy savings. Moderate climate applications achieve longer paybacks of 8 to 15 years. Cold climate applications may never achieve positive economics due to winter heating penalties. Federal and state tax credits sometimes support cool roof adoption, substantially improving economics in applicable markets. Utility rebates in hot climate regions further improve economics where available. Asunta Zevallos Fernandez, a Peruvian-American residential energy policy researcher, has documented how cool roof adoption delivers particularly favorable economics in southwestern states with extreme cooling seasons and modest heating seasons. Her analysis shows that Arizona, Nevada, Southern California, and similar regions can achieve cool roof paybacks under 5 years through cooling energy savings alone, with substantial additional benefits across continued service lives. The regional targeting of cool roof incentive programs reflects these documented performance variations, supporting concentrated adoption in highest benefit climate zones. The heat island mitigation benefits of cool roofs extend beyond individual homeowner benefits to include substantial urban environmental improvements. Dark roofs contribute to urban heat island effects that raise citywide temperatures by 5 to 10 degrees above surrounding rural areas. Widespread cool roof adoption reduces heat island intensity, producing citywide cooling energy reductions beyond individual building savings. Public health benefits from reduced extreme heat events complement energy savings. The environmental benefits support municipal and state cool roof policies that extend beyond individual homeowner decision-making. Dr. Felipe Espinosa Morales, a Mexican-American urban climate researcher, has documented how widespread cool roof adoption in major southern cities could reduce urban heat island effects by 2 to 4 degrees, delivering substantial cooling energy savings across entire urban areas. His research validates municipal policies, including California cool roof mandates for specific building types and Los Angeles cool roof incentive programs. The urban climate benefits support expanded cool roof adoption through public policy beyond pure homeowner economics. The integration with solar photovoltaic systems produces substantial synergies for homeowners, considering both improvements simultaneously. Cool roofs reduce ambient temperatures around solar panels, improving panel efficiency substantially compared to hot, dark roof surfaces. The combined improvements deliver greater benefits than either approach alone. Timing roof replacement with solar installation optimizes both investments through coordinated decision-making. The integration represents emerging best practice for comprehensive solar-ready roof design that maximizes both thermal and electrical performance. The metal roofing, particular characteristics deserve specific attention, given substantial market share growth. Standing seam metal roofs provide superior longevity of 40 to 70 years compared to 20 to 30 years for asphalt shingles. Infrared reflective coatings enable any color selection with good, cool roof performance. Metal roofs shed snow more readily than asphalt, reducing ice dam problems in cold climate applications. The combined longevity and performance benefits often justify substantial cost premiums for homeowners with long-term ownership horizons. The metal roof category particularly demonstrates cool roof technology value when combined with other performance benefits. Carmen Valladares Rodriguez, a Colombian-American residential roofing consultant who has specialized in metal roof applications across southern states, has documented how metal roofs with infrared reflective coatings achieve performance and longevity combinations that asphalt alternatives cannot match. Her client experience demonstrates that metal roofs often deliver lower lifetime costs than asphalt, despite higher initial investment through longer service lives and superior thermal performance. The life cycle economics support metal roofing adoption for homeowners with sufficient capital and long-term planning horizons. The tile roofing applications in Mediterranean and Southwestern architectural styles provide cool roof benefits alongside traditional aesthetic appeal. Clay tiles in traditional terracotta colors achieve reasonable cool roof performance through thermal mass effects alongside modest reflectance. Concrete tiles with infrared reflective coatings achieve superior performance while maintaining traditional aesthetics. The tile options particularly suit homes in regions with architectural traditions supporting tile roofing, integrating cool roof benefits with established aesthetic preferences. The research on long-term cool roof durability shows generally favorable results for quality products. Performance degradation from weathering averages 10 to 20% across typical service lives of 20 to 30 years for asphalt products. Metal roof performance degrades less than 10% across 40 to 70-year service lives. The modest long-term performance reduction preserves substantial benefits compared to conventional roof alternatives. The durability supports cool roof adoption as long-term investment rather than short-term improvement. The Energy Code integration has progressively supported cool roof adoption through performance requirements. California, Title 24 requires cool roofs for specific building types, including residential, multifamily, and commercial buildings. Florida Building Code includes cool roof provisions for specific applications. Other states have adopted or considered similar requirements. The code integration supports continued market growth beyond purely voluntary adoption, driving manufacturer investment in cool roof product development and availability. The professional installation considerations for cool roof products generally match conventional roofing installation requirements. Most roofing contractors can install cool roof products without specialized training beyond typical roof installation expertise. Product-specific installation details matter for achieving rated performance values, but fall within typical contractor capabilities. The installation simplicity eliminates specialized contractor availability limitations that affect many efficiency improvements, supporting widespread adoption through existing contractor networks. The ventilated cavity roof constructions combine cool roof benefits with ventilation approaches that further reduce heat transfer into attic spaces. Double-layer roof assemblies create air gaps between outer roofing and underlying substrate that enable convective airflow, exhausting absorbed heat before it reaches the primary insulation layer. The ventilated assemblies, combined with reflective outer surfaces, deliver substantially better thermal performance than either approach alone. The technology originated in hot climate traditional construction across Mediterranean and Middle Eastern regions, representing proven approach adapted to contemporary materials and assembly methods. Dr. Yasmin Farouk Mansour, an Egyptian-American building science researcher who has studied ventilated roof assemblies across hot climate applications, has documented how ventilated cool roofs can reduce ceiling heat transfer by 60 to 80% compared to conventional sealed roof assemblies. Her research validates comprehensive roof design approaches that address both solar absorption prevention and heat removal through integrated assemblies rather than isolated components. The ventilated cool roof approach represents emerging best practice for extreme hot climate applications where every possible performance improvement matters. The thermal mass interactions with cool roof performance deserve specific attention for homes with substantial attic or ceiling thermal mass. Dark roofs charge attic spaces with substantial thermal energy during daytime hours that continues radiating into living spaces during evening hours when outdoor cooling might otherwise reduce indoor temperatures. Cool roofs substantially reduce this thermal charging, enabling evening cooling to proceed more effectively. The thermal mass considerations affect diurnal cooling patterns in ways that static performance calculations may not fully capture, supporting cool roof benefits beyond peak cooling period measurements. The algae resistance characteristics of modern cool roof products address durability concerns affecting earlier generations. Copper-containing granules in premium asphalt shingles prevent algae accumulation that would otherwise degrade reflectance performance. Fungicide treatments in elastomeric coatings provide similar protection for coated applications. The algae resistance preserves initial reflectance values more effectively than earlier products, improving long-term performance retention substantially. Consider what cool roof technology means for hot climate homes approaching roof replacement decisions seeking to improve cooling efficiency while maintaining appropriate aesthetic options. The cooling energy reductions of 15 to 30% deliver substantial operational savings across extended roof service lives. The modest cost premiums of 10 to 30% over conventional alternatives produce favorable paybacks in hot climate applications. The aesthetic flexibility through infrared reflective pigments eliminates the stark white appearance that deterred earlier adoption. The product variety across asphalt, metal, and tile categories suits diverse aesthetic preferences. The long-term durability preserves substantial benefits across 20 to 70-year service lives depending on material choice. The urban heat island mitigation provides environmental benefits beyond individual homeowner considerations. The solar photovoltaic integration synergies extend benefits for comprehensive home improvements. The utility rebate availability reduces net costs in supportive markets. The code integration supports continued market growth and product development. The installation simplicity eliminates specialized contractor limitations. The timing with inevitable roof replacement captures benefits without incremental capital investment. The question isn't whether cool roof products deserve consideration during hot climate roof replacement projects. The question is why traditional dark roof preferences continue to dominate consumer decisions despite well-documented cooling energy penalties and modern product options that address earlier aesthetic concerns. The answers involve consumer education gaps, marketing priorities favoring traditional products, and contractor recommendations based on familiar products rather than comprehensive performance analysis. For hot climate homes approaching roof replacement decisions, cool roof products represent one of the most cost-effective cooling efficiency improvements available in contemporary residential markets. The low-slope and flat roof applications of cool roof technology often produce even greater benefits than sloped roof applications. Commercial and residential low-slope roofs with reflective membranes can achieve solar reflectance values exceeding 85%, substantially better than even premium sloped roof products. The cool roof benefits in low-slope applications combine with the larger thermal mass of flat roof construction to deliver particularly strong cooling performance. Multi-family and commercial applications with flat roofs therefore represent especially attractive cool roof opportunities beyond single-family residential contexts. Takako Shimizu Nakamura, a Japanese-American commercial roofing consultant, has documented exceptional cool roof performance in flat roof applications where reflective membranes can be applied more easily than in complex sloped residential roofs. The roof ventilation coordination with cool roof installation affects overall attic thermal management. Cool roofs reduce attic heat gain substantially, reducing the ventilation requirements that address attic heat accumulation. Proper coordination between cool roof selection and attic ventilation sizing optimizes overall thermal management while avoiding over-specification of either component. The integrated design approach produces better outcomes than treating roof selection and ventilation as independent decisions. The radiant barrier integration with cool roof installation produces additional synergistic benefits. Radiant barriers installed under roof decking reflect radiant heat that cool roofs didn't reflect at the outer surface, providing secondary heat rejection. The combined systems address heat gain through multiple mechanisms, achieving superior total performance. Installation costs for radiant barriers during roof replacement are modest compared to standalone retrofit installations, making combination approaches economically attractive during inevitable roof replacement projects. The historic preservation considerations in traditional homes sometimes affect cool roof product selection. Historic district regulations may require specific roofing materials or colors that constrain cool roof options. Modern, infrared reflective pigments in traditional colors often satisfy both historic preservation requirements and cool roof performance goals simultaneously, expanding the compatibility range substantially. The historic preservation compatibility supports cool roof adoption in contexts that might otherwise exclude newer technologies. The warranty considerations for cool roof products generally match conventional roof product warranties, providing consumer protection equivalent to familiar alternatives. Asphalt. Cool roof shingles typically carry 20 to 30-year material warranties comparable to conventional shingles. Metal cool roof products carry 30 to 50-year warranties. Elastomeric coatings carry 10 to 20-year warranties depending on product quality and application specifications. The warranty structures eliminate consumer protection concerns that might otherwise affect adoption of newer products. The coastal climate considerations affect cool roof product selection through salt spray and wind resistance requirements. Metal cool roof products with appropriate coatings resist coastal corrosion substantially better than asphalt alternatives. Wind resistance ratings for cool roof products generally match conventional product options, eliminating performance compromises for coastal applications. The climate-specific product selection supports cool roof adoption across diverse American regional contexts without requiring generic product compromise.